This is the second of two videos on section 5.5. In this video, I'm going to be working through several examples where we work through substitution and practice different ways that substitution can work for integrals. So remember, the substitution rule is basically the reverse of the chain rule. It says that if we've got a function inside a function, so we've got f of g of x, and we're also multiplying by g prime of x, then we can reverse the chain rule and end up with capital F of g of x plus c, where capital F is any antiderivative of little f. So to put this in practice, this is the rough outline that I gave you in the last video. The first thing we want to do is identify an inside function u, figure out what that g of x is, figure out what that inside function is. And then our goal is to get the g prime of x, or the u prime, next to the dx. And the idea is that u prime times dx, that's what we call du. And then we're going to rewrite our integral in terms of u and du, and there should be no extra x's at this stage. If there are any x's left over at that point, then the substitution didn't work, and we'll talk about some examples of that. Then we're going to evaluate our new integral, and then we're going to rewrite the answer back in terms of the original variable x. Okay, so let's take a look at this one. So we've got x to the fourth times x to the fifth plus 6, all raised to the seventh power. So the basic idea is that you want to look for the most complicated term of the function and then let u be the thing inside of it. It's only a rule of thumb, but it's a good way to think about what a good u choice is going to be. So again, look for the most complicated part, and then u is the thing inside of that. So in this case, the most complicated part is this x to the fifth plus 6 all raised to the seventh power. And so the thing inside of that is the x to the fifth plus 6. So we've identified our u. Now, we don't know that this is the correct u yet, so the next thing that we need to do is figure out what du is. So du is the derivative of u, which is 5x to the fourth, multiplied by dx. And now this gives us a goal. So the goal is get a 5x to the fourth next to the dx. That's what we want to have happen here. All right, well, that's where the extra x to the fourth that we have in our function is going to come into play. So I'm going to switch the order of my multiplication. So I've got x to the fifth plus 6 to the seventh, multiplied by x to the fourth. And I say to myself, gosh, I really wish that was 5x to the fourth. I've got x to the fourth, that's great, but I'm missing the 5. So here's the trick we're going to do. And we're going to be doing this trick a lot, so kind of might want to slow down or rewatch the video a couple times to sort of follow what I'm doing here. So I say to myself, okay, I really need there to be a 5. So I'm just going to put a 5 in. But I can't just do that. I can't just put in the 5. Because if I do that, then I've multiplied my function by 5, and it's not the same function anymore. So to balance out multiplying by 5, I'm also going to multiply by 1/5. So that if I do both of those things, I haven't changed the function. It's the same function, and I've just done something clever to give myself the 5x to the fourth that I was looking for. Now, this 1/5, I needed that to be there so that I balanced out the 5, but I don't actually want it to be in my function. And because that 1/5 is a constant, one of the properties of integrals that we talked about is that I can pull that constant out, and I'm going to write it out front of my integral. So what's left inside my integral is x to the fifth plus 6 all raised to the seventh, multiplied by 5x to the fourth dx. And now I'm ready to convert this to the u integral. 5x to the fourth dx, that's du. X to the fifth plus 6 to the seventh, well, u was x to the fifth plus 6, so this becomes u to the seventh. So my new simpler integral is 1/5 times u to the seventh du. And that's a relatively easy integral because we can just use our power rule. We add 1 to our power, we get u to the 8th, plus c because we took an antiderivative. And then the last thing to do is to write this in terms of the original variable x. 1/5 times 1/8 is 1/40th, and then u was x to the fifth plus 6, so that's now raised to the 8th power, plus c, and there's my final answer. And remember, with antiderivative problems, we can always check our answer by taking the derivative. So if you take the derivative of this function, you're going to use the chain rule, because the chain rule is the derivative version of the substitution rule. So we're going to use the chain rule, and then we're going to get back our original function. So let's do another example. So here we have the integral of cosine cubed of x plus sine of x. So first things first, let's remember that when we write cosine cubed of x, what that really means is cosine of x cubed multiplied by sine of x. And again, when we look at this, we're going to think to ourselves, okay, what's the most complicated term here? What's the most complicated part of this function? And this cosine of x cubed, that's the most complicated part. So we're going to let u equal that most complicated term. We're going to let u equal the thing inside that most complicated term, which is cosine of x. So we don't want to let u be the entire most complicated term. We don't want to let u equal cosine of x cubed. That's going to be too complicated. That wouldn't let our substitution work. We want that to be the inside function. So then du is the derivative of cosine of x, which is minus sine of x. And we're so close to that. We've got a sine of x next to our dx, but what we're missing is the negative sign. So we're going to do a similar trick to what we did in the previous problem. So I'm going to stretch apart my integral here, leave some space, because what I really need there to be next to my sine of x is I need there to be a minus sign. Well, a minus sign like that is multiplying by negative 1. So to balance out multiplying by negative 1, I have to divide by negative 1. So that's going to be the general trick. If we're missing a constant multiple, whether it's a 5 like it was in the previous problem or a minus 1 like it is in this problem, we're going to be able to put that constant in as long as we also put in 1 over that constant. Now the 1 over the constant, the one that we didn't want, that's going to go out front. So this is going to become negative 1 out front of my integral times the integral of cosine of x cubed multiplied by negative sine of x dx. So this 1 over negative 1, 1 divided by negative 1 is negative 1, so that's where that ended up. Okay, so now we're ready to convert this to a u integral. So cosine of x cubed, that's u cubed, minus sine of x dx, that's du, and so this becomes negative 1 times the integral of u cubed du. That's a pretty easy power rule, so it's going to be negative 1 times 1/4 u to the 4th plus c, and then the only thing to do is put back in our original variable. So that's negative 1/4. U was cosine of x, so that's cosine of x to the 4th power plus c. Just to pause for a bit on this problem, we're done, but I just want to talk about it a little bit more. A common question that I often get in these kinds of problems is, what happened to the sine of x, right? You're looking back at the original function, and you see this sine of x, and then you look at the answer, and you don't see a sine of x. And you think, well, what happened to that? Where did that go? Well, where it went was it got absorbed into the dx to become the du, right? So this step right here, when we say to ourselves, okay, du is u prime times dx. U prime is negative sine of x. And so because we have the u prime next to the dx, we can reverse the chain rule. When we do a derivative with the chain rule, we have that extra second step where we have to multiply by the derivative of the inside function. We're undoing that step. So because we have the derivative of the inside function, when we reverse it, it disappears. All right, let's do another example. So this time we have a definite integral. So we have bounds. We're integrating from 0 to 2, and I'm going to talk a little bit about what we do with that. But for the moment, we're just going to ignore them. We're just going to treat this just like it was any other function. So first, another thing that looks a little weird about this function is that we have a dx divided by 2x plus 3 squared. So this is a common notation. It's really just sort of a space saver. But what this really means is that my function is 1 over 2x plus 3 squared. And then the dx is over here. So very often when we have a fraction like that, you'll see the dx get sort of slid up to the top of the fraction. It's just an optional notational type of thing. So because it's a little bit confusing sometimes, I'm going to move it off and put it off to the side. Okay, so we have 1 divided by 2x plus 3 squared. Remember that we're looking for our u to be an inside function. So in this case, it looks like that inside function should be 2x plus 3. And so my du is going to be 2 dx. Now a 2 is going to be pretty easy to come by because all we're going to need to do is put in a 2 next to my dx, and then I also have to put in a 1/2 to balance that out, and then the very next thing I'm going to do is move that 1/2 out front. Now, once we start getting good at this, we can just do that all in one step. So I'm just going to go ahead and do that. So I'm going to put in the 2 inside my integral here, and then I'm going to put the 1/2 out front. All at once. But what I've really done, if I didn't want to skip steps, is I put in a 2 and a 1/2, both on the inside, and then pulled out the 1/2. All right, so now I'm ready to convert this from my x integral to my u integral. 2 dx, that's my du, and 1 over 2x plus 3 squared, that's 1 over u squared. So my new integral is 1 over u squared du. Now notice that I left the bounds off of my integral. And the reason is because the numbers 0 and 2 are values of x, right? So this is x equals 2 and x equals 0. So if I wrote a 0 and a 2 on this new u integral, then the assumption would be that those are u values, but they're not. Those are x values. So what I have to do is I have to compute the new u values that correspond to my original x values. And the way that I'm going to do that is by using my formula for u. So I've got two values that I started with. I've got x equals 2 on the top, and when x equals 2, u is equal to 2x plus 3, which is 2 times 2 plus 3, which is 7. So my upper bound on my new u integral is not 2, now it's 7. And then what about the lower bound? Well, when x equals 0, u is 2x plus 3, which is 2 times 0 plus 3, which is 3. So the lower bound becomes 3. And now I'm going to keep going like I did before. Okay, so how do I take the antiderivative of 1 over u squared? Let's rewrite that as u to the negative 2. Then I can use my power rule. I'm going to add 1 to my power, divide by the new power. And then just like any other definite integral, I'm going to plug in 7 and I'm going to plug in 3 and subtract. And notice here that I don't need to go back to x's because I completely converted my integral over to u's. I don't need to go back to those original x values, 0 and 2, because I found the corresponding u values, 7 and 3. So I've got minus 1 over u, right? So this is a minus 1, and this is 1 over u. So I've got minus 1 over u, and I need to plug in 7, and I need to plug in 3 and subtract. So I got negative 1 over 7 minus negative 1 over 3. That's negative 1/7 plus 1/3, which is going to be 4/21. And so that's the value of my integral. Okay, so when you do a substitution in a definite integral, you have to use your formula for u to change the bounds from the original x values to the corresponding u values. So the disadvantage of that is that it feels like you have to do more work, right? That you have to plug in those values and get the u values, which is something that we didn't have to do for the indefinite integrals. But the advantage is that at the end of the problem, we get to skip the step where we go back to the x's, right? So we've got our new u values, so we can just go ahead and plug in those values. So it actually ends up being a little bit less work to do this. Okay, let's do another example. So we've got the integral from 0 to pi over 2 cosine squared dx. So again, we look at this and we think to ourselves, okay, I want my u to be my inside function. So I'm going to let u equal the cosine of x, because that's the thing inside, because this is cosine of x squared. And then my du is going to be the derivative of cosine x minus sine of x dx. This is pretty similar to a problem that we did earlier, but now the problem is that I don't have a sine of x in my problem. The negative sign, that's not going to be a problem, right? The negative 1, I can get that using the trick that we've been using a couple times now. But where is a sine function going to come from? What I can't do is put in sine of x and 1 over sine of x, because if I tried to do that, I would have an extra 1 over sine of x in my problem, and I wouldn't be able to pull that 1 over sine of x out. Let's see what that might look like. If I try to do that, 0 to pi over 2, I've got cosine of x squared, and I say to myself, okay, what I really want is minus sine of x, so I can get that as long as I put in a 1 over minus sine of x. And so far I haven't made any mistakes, but now the problem would be, what I would want to do is to get that negative sine of x out of my integral, and I can't do that, because this right here is not a constant, and I can only do that with constants. So we would get stuck. And so what that tells us is that this is the wrong substitution. So this substitution didn't work. And that will happen sometimes. Sometimes you'll have a guess for what you think the substitution should be, you try it, and you realize that it doesn't work. This is one of the things, I'm going to talk about this at the end of the video, but this is one of the things that makes integration a little bit more challenging than differentiation, than taking derivatives. Okay, so if that's the wrong substitution, what do we do? Well, it turns out that what we need here is a trig identity. And the trig identity that we need is that the cosine squared of x is equal to 1/2 times 1 plus the cosine of 2x. And so if we replace that, we get the integral from 0 to pi over 2, 1/2 times 1 plus the cosine of 2x. I'm going to let u equal 2x here. du is going to be 2 dx. So this 1/2 that's already in the problem is going to get put out front. I've got 1 plus cosine of 2x. I'm going to put in a 2 because I needed 2 for my dx, which means I'm going to have to put another 1/2 out front to balance out that 2. And then I can convert my integral. So I've got 1/4 integral, I'll change my bounds in a second, plus 1 plus cosine of u du. What are my new bounds? Well, my old bound was x equals 0. So when x equals 0, u is going to be 2 times 0, which is 0, so my lower bound is still 0. When x equals pi over 2, u is going to be 2 times pi over 2, which is pi. So my new upper bound is pi. All right, now we're ready to take our antiderivative. Okay, so the antiderivative of 1 is u. Antiderivative of cosine u is sine u, and that's because the derivative of sine u is cosine u. And then I'm going to plug in pi and 0 and subtract. So I've got 1/4 pi plus sine of pi minus 0 plus sine of 0. Using a little bit of trig knowledge or our calculator, we can see that sine of pi is 0 and sine of 0 is 0. So the only thing that's not 0 inside those brackets is pi. So we get pi over 4. Okay, so the couple tricky things here. One is that there seemed to be a natural substitution to try that ended up not working. And then the other tricky thing is that what did end up working was a trig identity that many of you probably weren't too familiar with, right? That's a trig identity that might be a little bit obscure and might not be one that you remember. So this is going to be the kind of thing that's going to happen sometimes. So in general, the trig identities that you might need if you've got cosine squared or sine squared look like this. So the one that we already talked about, cosine squared of theta is 1/2 times 1 plus cosine 2 theta, and then sine squared of theta is 1/2 times 1 minus cosine of 2 theta. So jot those down somewhere prominent. You know, if you've got a list of trig facts or trig identities, things like that, add those to the list if they weren't there already. But those are things that are just things that are available for us to think about. Okay, one more example and then we'll kind of wrap up here. So antiderivative of 1 over 1 plus 4x squared. So again, we're thinking to ourselves, okay, let's let u be the thing inside the most complicated term. Well, there's only really one place where x's live in this function, and that's the denominator of this function. So the sort of natural thing to try would be to let u equal 1 plus 4x squared. So du would be 8x dx. And again, the 8 is not going to be a problem. I can put in an 8 and a 1/8, but the x is going to be a problem. I don't have an extra x lying around this function to make this substitution work. Again, kind of like the previous problem. If I try that, if I write an 8x and a 1 over 8x, again, that's fine, but this 1 over 8x I cannot take out of my integral because it's not a constant. So again, what that means is that this is the wrong substitution, right? It was the natural thing to try, but it just ended up not working. And this is another example where we're going to have to think outside the box a little bit. So I'm going to take this 1 over 1 plus 4x squared, and I'm going to rewrite it as 1 over 1 plus 2x parentheses squared. Right, if I square 2x, that means I'm squaring the 2 and I'm squaring the x, so I get 4x squared. And then the substitution I'm going to do is going to be u equals 2x, du equals 2 dx. And if you're not yet sure how this is going to work out, keep watching. So the 2, that's not going to be a big deal. I can put in a 1 plus 2x squared. I've got that on my denominator. I'm going to put a 2 inside my integral and a 1/2 outside my integral. That one I can do because 1/2 is a constant. And then when I switch this over to a u integral, I get 1 over 1 plus u squared times du. And now hopefully you recognize 1 over 1 plus u squared as the derivative of inverse tangent of u. So what we had to realize is that in our original function, 1 over 1 plus 4x squared, we think to ourselves, wow, if I could get rid of that 4, then this would look a lot like inverse tangent. And the way to do that is with a substitution. So we've got one more step because this is an indefinite integral. We've got to put back in what x was. X was 2x, so this is 1/2 times the inverse tan of 2x plus c. Again, a tricky one. Okay, so in general, integration is more challenging than differentiation because it's not always clear what it is we have to do. So with differentiation, we have rules and we sort of know what rule we have to apply in different situations. If it's a product, we use the product rule. If it's a quotient, we use the quotient rule. With integration, there's no clear indication of what strategy we need to employ in any given problem. So the sort of the comic that I've got here is a little bit of an illustration of that. So unfortunately, the thing that we have to do with integration is work through lots of examples in practice and see the different strategies in action and develop an intuition as to which strategy is likely to work in any given problem. So as many practice problems on this stuff as you can do, you'll get better at it.